Let knowledge flow like a river, without any hindrance. Don't make it like a stagnant pool. Hello everyone. Once again, I am PS Chatterjee with you. A warm welcome back to my channel. You are now watching Structural Design Only, a channel with a different vision. We are continuing our journey into the design of crane gantry girders. If you missed part 1, I highly recommend checking it out first to get the full context. Today's video is titled, Design of Crane Gantry Girders, Magic Reveals with Excel Automation, Part-02. In this session, we will focus on the practical application of Excel-based automation for gantry girder designs with base spans of 4.5 meters and 6 meters, and crane bridge spans ranging from 9 meters to 30 meters. We will cover crane lifting capacities from 1 metric ton, up to 20 metric tons. Along with the structural logic, we are going to use Excel VBA for seamless data refreshment and report transfers. To give you the most effective view of the process, I prepared this as a PowerPoint presentation. Before we dive in, I believe this video will truly supplement your knowledge. If you find value here, please consider supporting my work. Subscribing, regular viewing, liking, sharing and commenting are the fuel that keeps this channel running. They are the true remuneration for the hard work put into these technical tutorials. Please watch the video in full to get the complete technical picture. If you'd like to support the creation of more content and receive these free Excel sheets, consider making a contribution that fits your budget via the UPI ID in the video description. However, if you feel this video provides no value, feel free to press the dislike button. But remember, disliking without an explanation is a verdict without judgment. Please leave a comment explaining why, as your feedback is more valuable to me than a like. Now, let's get started by looking at the required data tables we need to develop, one by one. We begin by establishing our base parameters. As you can see in tables 01 and 02, we have organized the core crane data, categorizing crane capacities ranging from 2 to 20 metric tons. These tables serve as the foundation of our model, mapping out critical values like self-weights and wheelbase dimensions. Precision at this stage is vital, as it ensures the accuracy of all subsequent calculations. Now, let's look at the selected values block. To fetch the self-weight of the crane bridge, we use a dynamic VLOOKUP function. The lookup value is the crane capacity, WC. WC is the defined name of the crane capacity, but since the data is two-dimensional, we use the match function to determine the correct column index. The match function looks for the bridge span, LB, within the range B3 to I3. This allows the formula to pinpoint the exact intersection of capacity and span. You'll also notice that we've wrapped the entire formula in an if statement. It only activates if check 1 returns OK. This is our first automated checkpoint, it verifies that all primary design data has been entered before the model proceeds with calculations. We apply this same VLOOKUP logic to retrieve the crab weight, rail section, hook approach, and wheelbase dimensions. By using the crane capacity, WC, as our primary key, we ensure that every selected value is perfectly synchronized with our design requirements. Let's move to the next slide to overview data tables 03, 04, and 05. Now, we will overview data tables 03, 04, and 05. Moving to table 03, we expand our database to include detailed steel section properties for ISMB and ISWB. We have meticulously categorized these sections, providing essential geometric data such as depth, flange width, and moment of inertia. By having this data pre-linked in Excel, we eliminate manual lookups and drastically reduce the risk of human error during our stress analysis. Shifting our focus to table 04, you will find the same level of detail, but this time for ISMC channel sections. Following that, table 05 covers IST sections and steel plates. For the properties of ISMB, ISWB, ISMC, and ISMT, we consult the IS Handbook for Steel, SP6. A crucial tip for young engineers: when incorporating these values, you must be extremely careful with the units. In SP6, many properties are listed in centimeters. For our design model, we must convert these units to millimeters to maintain consistency. Finally, regarding the steel plates in table 05, if we know the thickness and width, we can calculate the properties easily. You'll notice these values are highlighted in red. This indicates they are calculated values rather than static lookups. In the next slide, we will move on to overview data tables 06, 07, and 08. Now, we are going to overview data tables 06, 07, and 08. These are auto-generated tables. To differentiate them from the static tables explained previously, the data is shown in blue. You can think of table 06 as a bucket of selected data. If you look at the last two rows, the first cell of the third row is currently blank because we have selected a plate rather than an ISMT. When an ISMT is selected as an additional bottom section, those cells will populate automatically. Presently, those values are 0, which is why we find data in the fourth row for the plates instead. This represents our first screening of the data. Next, table 07 acts as a second screening. This table consolidates the specific properties for the chosen additional section, whether ISMT or plate, into a single calculation row. Finally, in table 08, we calculate the combined plastic properties of the entire section. In this segment, we bridge the gap between properties and application. These tables act as our lookup engine. When you select a section in the dashboard, Excel automatically pulls the corresponding structural properties. I have created a separate sheet named Data to house tables 01 through 08. Now that we have reviewed these final auto-generated tables, 06, 07, and 08, we are finished with this sheet. In the next slide, we will overview another data tables in the sheet, named as dashboard. Let's take a look at that table. Now, we are looking at data table number 09, which is located right here on the dashboard. This table is the engine behind our dynamic drop-down menus. Its primary job is to ensure that the choices you see are always relevant to your specific design. Notice the green highlighted row. This is driven by conditional formatting that directly depends on the I-beam or main girder you have selected. As you change the main girder section, this green highlight shifts automatically to guide your next steps. Within this highlighted green zone, the system provides specific guidance. It shows our recommended channel sections and the appropriate plate widths for that particular I-beam. This eliminates guesswork and helps in controlling deflection more effectively. Essentially, this table acts as a smart filter, narrowing down the vast library of steel sections into a refined list of recommended and alternative members. This ensures that the selections you make in the drop-downs are structurally sound and optimized for your gantry girder design. Now, let's move toward the Excel dashboard. Welcome to the heart of the automation, the Excel dashboard. At the very top, we have the project header. This area captures the essential project identities, currently displaying, detail design and calculation for Crane Gantry Girder of capacity 7.5 metric ton, Gantry Girder span 6 meter, Crane bridge span 30 meters, and operation type EOT, which stands for electrically operated trolley. This is a dynamic heading. As you change the data in cells E4 through E7, the heading will automatically adjust itself to reflect the new parameters. Just below this heading, in row 2, I have included professional tracking details such as the reference number, company name, and the structural engineer's credentials. This ensures that every generated report is properly documented and ready for professional submission. Input parameters and section selection, located in the center left, we find our primary input zone for design and partial safety factors. Here, you define essential material properties such as yield stress, tensile stress, and elasticity. You also set the partial safety factors for both materials and loads, ensuring the design adheres to Indian standards. Just to the right of these inputs, in cells E9 through E13, we select the specific sections for the Crane Gantry Girder. This is where the dynamic drop-downs we discussed earlier truly come to life. By selecting the ISMB, ISMC, and extra member dimensions, whether a plate or an ISMT, the entire sheet instantly recalculates every design parameter. Notice the visual cross-section on the far left. This provides a real-time preview of your combined section as you build it. This is a dynamically linked picture, and it's actually one of my favorite features in this Excel tool because it gives you immediate visual feedback on your engineering choices. Controls and Automation. Now, look at the two buttons on the middle right of the dashboard. Before starting any new design, it is always best to click the Refresh button. To prevent any accidental clicks, I've programmed a VBA confirmation that will ask you to confirm with a yes or no. Simply select yes to reset the data for your new project. Once your calculations are complete and you are satisfied with the design, you can click the Send Report button. This automatically transfers and stores all your design data into the dedicated sheet named Reports for final documentation. As for the remaining values shown in blue, these are all auto-generated data points. They handle the internal engineering logic without requiring any manual input. Without investing any more time here in the slides, let's dive into the actual Excel sheet and see the automation in action. Let's go. Now we are in the actual Excel sheet, exactly where we left off in the PowerPoint presentation. Let's perform a test. Imagine you have just graduated and, as a young structural engineer, you've received your first assignment: design a crane gantry girder with a 1 metric ton capacity, a 4.5 meter gantry span, and a 9 meter crane bridge span. With this automated sheet in your hand, how long do you think it will take to solve? I believe it won't take more than 5 minutes. Let's check the clock. To start, we must clear all previous design data. As I mentioned earlier, we click the Refresh Automation key. Notice the warning: Excel needs to know if this was an accidental or intentional click. Since this is intentional, we will select Yes on the prompt. Look at that, we've successfully cleared all previous data with a single stroke. The auto-generated cells have turned blank. Isn't that the magic of Excel logic? Notice our first checkpoint, Check Data Points, has turned from green to yellow, signaling that the sheet is ready for new inputs. Also, look at the dynamic heading: it has reset from the 7.5 ton description to a simple, clean title. Now, I'll enter our first set of preliminary data: 1 metric ton capacity, 4.5 meter gantry span, and a 9 meter crane bridge span. For our second set, we will keep the main girder as ISMB 300. I'll select an ISMC 175 for the channel, and in the Extra Members section, I'll select No Extra. Immediately after entering this data, our checkpoint shows OK once again. Observe the section profile in the top left corner. In this specific combination, there is no plate at the bottom. Finally, at the bottom right, we see the result. Overall design is perfectly okay with a total weight of 291.75 kilograms. Now, be honest and write in the comments: how many minutes did we actually spend on this design? Now, I am going to send these results to the sheet named Report. To do that, we click the VBA macro-enabled key, Send Report. Once again, you'll notice the safety warning. Excel needs to confirm if this was an intentional action. Since it is, we will select Yes on the prompt. Now, Let's shift our focus from the dashboard to the report sheet. Here, we see the complete report for the same gantry girder. However, notice that the layout and values are now formatted specifically for our client, clean, professional, and ready for submission. Now, seeing your prompt delivery on that first assignment, your client has handed you a second, more complex task: design an EOT crane gantry girder with a 5 metric ton capacity, a 6-meter gantry span, and an 18-meter crane bridge span. Your confidence barometer should be hitting the green zone now. Once again, we start by clearing the previous data. Click the refresh key, confirm the VBA prompt with a yes, and watch the magic of Excel logic at work. The auto-generated cells turn blank, and the dynamic heading resets to a clean title, ready for your new inputs. Notice the checkpoint has turned yellow, prompting you to check data points. Let's enter the preliminary data: 5 MT capacity, 6 M gantry span, 18 M bridge span, and EOT operation. The heading updates instantly, but look at the profile picture. A prompt appears saying, "Please select all the data points." This is our cue for the second set of data. Initially, you try the same sections as before: ISMB 300 with an ISMC 175 and no extra members. The checkpoint shows OK and the profile updates. However, look at the bottom right. The total weight is blank, and a new message appears: check allowable deflection. Here is the problem: your allowable deflection is 8 mm, but the calculated deflection is 14.27 mm. To fix this, you increase the channel section from 175 to 200. The deflection drops to 13.11 mm, but it's still not safe. Out of curiosity, you switch the operation type from EOT to HOT, hand-operated trolley. The calculated deflection drops to 12.12 mm, much closer to the allowable limit, but still not enough. So, you switch back to EOT, change the ISMC 200 back to 175, and try a larger main beam, the ISMB 350. Wait. Look at the screen. The ISMC 175 has instantly turned yellow with red strike-through text. This is the system's compatibility warning, telling you that an ISMC 175 cannot be properly fitted onto the flange of an ISMB 350. To eliminate this error, you revert to the ISMB 300 and decide to use an additional section instead. First, you try an ISMT. Notice the checkpoint turns yellow because the size hasn't been selected yet. Once you select ISMT 200 from the drop-down, the checkpoint turns green, signaling a valid input, but even with this addition, the design is still failing the deflection check. Finally, you switch the extra member to a steel plate. You start with a 160 mm width and 10 mm thickness. Still failing. You increase the thickness to 16 mm. Boom. the message changes to overall design is perfectly okay with a deflection of 6.76 millimeters. But as a structural engineer, you want to optimize. You notice the weight is 469.46 kilograms. You ask yourself, can I reduce this weight? You try increasing the plate width to 200 millimeters and reducing the thickness to 10 millimeters. Look at the result. The design is still perfectly okay. The deflection is 7.86 millimeters, and you have optimized the section beautifully. The weight has now been reduced to 451.85 kilograms. Now, we click Send Report. Confirm the intent with a yes on the VBA prompt. We shift our focus to the report sheet, and there it is, a clean, professional document formatted specifically for your client and ready for submission. Now, be honest. And write in the comments, have you ever seen this type of high-speed, crazy design sheet anywhere else in the digital world? Now, we are on the last lap of this video. By now, your performance has made you an adroit industrial design engineer. Your client has just assigned you a truly complex task: design an EOT crane gantry girder with a 20 metric ton capacity, a 6-meter gantry span, and a 30-meter crane bridge span. To you, this is now child's play. But a word of advice: don't let your clients see that. Tell them, this is one of the most critical jobs an engineer can handle. I'll need to spend significant time on this. Negotiate your consultancy fees accordingly. Now, jokes aside, let's focus on the design. We start by clearing the previous data. Click Refresh and confirm with Yes. The dynamic heading resets, and the checkpoint turns yellow, prompting, check data points. Let's enter the new parameters: 20 mt capacity, 6 m gantry span, 30 m bridge span, and EOT operation. The profile picture immediately prompts you to select all data points. Trial 1, you start with a combination of ISMB 400 and ISMC 250 with no extra members. The profile updates, but look at the bottom right. The weight is blank, and we see two warnings: check interaction ratio and check allowable deflection. The interaction ratio is 1.46, well above the limit of 1.0, and the deflection is 12.28 millimeters, far exceeding the 8 millimeters limit. We must alter the section. Trial 2, you move up to an ISMB 450. You'll notice the ISMC 250 is no longer compatible, so you switch to an ISMC 300. This successfully negotiates the deflection, but the interaction ratio is still above 1.0. You might think, let's try a larger channel, the ISMC 350. But look closely. Adding a larger channel actually increases the interaction ratio here. Why? Because structural engineering is about balance, not just adding more steel. A heavier channel shifts the center of gravity and increases the dead load. If the section becomes too top-heavy, the gain in strength is swallowed up by the shift in the neutral axis. To fix this, you move back to the ISMC 300. Trial 3, you select an ISMB 500 while keeping the ISMC 300. Now, look at the status. Overall design is perfectly okay. The weight for each gantry is 760.24 kilograms. You are now a professional, and since you've secured your professional fees, it is your duty to provide the best value to your client. But, how? By spending a few extra minutes to optimize the weight. The final optimization, you decide to reduce the main combination size and instead add a steel plate at the bottom. You revert to the ISMB 400 and ISMC 250. But this time, you add a 180 mm wide, 12 mm thick plate as an extra member. Boom! The message changes to overall design is perfectly okay and you have slashed the weight from 760.24 kilograms down to just 629.36 kilograms. That is a massive saving for your client. Finally, click Send Report, confirm with Yes, and once those consultancy fees are settled, send over this clean, professional document. You've just turned a complex engineering challenge into an optimized, expert solution. Today, we conclude our Excel automation for Crane Gantry Girders series. But before we finish, I want to share what's coming next. To complete this technical journey, I will soon be developing a new automation tool for columns under truss systems containing gantry girders, specifically focusing on crane case roof trusses as per SP 38. Please make sure to watch my videos in full to get the complete technical picture. If this video helped you, please give it a thumbs up. If you value this type of content, consider subscribing to stay updated on our latest design series. And remember, sharing knowledge is enhancing knowledge, so please share this video link with your fellow engineers. If you would like to support the creation of more technical content and receive these Excel sheets for your own use, please consider making a contribution that fits your budget. You can find my UPI ID in the video description. However, if you feel this video provided no value, you are welcome to press the dislike button. But remember, a dislike without an explanation is a verdict without judgment. Please leave a comment explaining why, as your feedback is far more valuable to me than a like. If you feel this tutorial has supplemented your knowledge, please consider supporting my work. Subscribing, regular viewing, liking, and commenting are the fuel that keeps this channel running. To me, your engagement is the true remuneration for the long hours put into these technical tutorials. Your support genuinely helps me improve how I share engineering knowledge with all of you. Thank you for your cooperation and your continued encouragement. Goodbye for now, and I will see you in the next video.